I hope you are all ready for the last session of this conference. And this session is on Bayesian network development, and it's too short for the number of developments or for the length of the talks that we should have. But we do what we can, and it's mostly about dynamic Bayesian networks, and they were talked about a little bit yesterday, and about expert elicited either structure of a model or parameters of the model. And our first speaker is Paul, and he's a senior lecturer in the School of Mathematical Sciences and an associate investigator in the Center for Data Science, an ARC Center of Excellence in Mathematical and Statistical Frontiers. He leads several collaborative projects between data science researchers, applied researchers, and industry practitioners, and his passion for collaboration has been recognized with 2 Vice Chancellor's Awards for industry engagement and student mentorship on engaged research. Key methodological interest areas for Paul include Bayesian statistics, non-homogeneous state-space models, dynamic Bayesian networks, and machine learning. And Paul will combine a few of those in the talk today, and he'll talk about dynamic Bayesian network inferencing for non-homogeneous complex systems. So Paul, whenever you're ready, if you could share your screen and start your talk.
Well, thank you everyone for having me. Today I'd like to share a bit of our work that we did. This is in JISSC on dynamic Bayesian network inference, especially how to do inference for non-homogeneous models. So this is collaborative work with Kerry, of course, and ecologists and marine biologists, Julian, Gary, and Catherine for our case study. So we're associated with ASMS, the Center of Excellence for Maths and Stats, and the QED Center for Data Science. Right, so a bit about the case study. So this was developed for seagrass ecosystems. Like, why are we even interested in doing non-homogeneous inference? So this is the motivating example. So a bit about seagrass. It is a critical habitat for fish, endangered species like dugongs and turtles, provides 1.9 trillion ecosystem services. So imagine your lawn in your garden, put that under the ocean, that's basically seagrass. It's a flowering plant. Okay, and interestingly, it stores more carbon per hectare than the Amazon rainforest. So it's quite important. But as with all good things, it's declining at an incredible rate since 1980, and there's an urgent need to better manage anthropogenic human threats to this critical ecosystem. And our particular case study focused on dredging, but the model can be applied to other anthropogenic disturbances as well. So basically, we want to have the top part with nice, healthy seagrass rather than the bottom part. And the way we went about dealing with this complex system was with a dynamic Bayesian network. So in our DBN, we're interested in evaluating the probability of chute density at different points in time. So our model had monthly increments because that related to the growth and biological timescales for seagrass. This is literally watching the grass grow, right? And we're interested in the probability of chute density in different states given particular species or genera, basically. Location characteristics, environmental disturbances, such as relating to light. So in our diagram here, we've got our response metrics. So predominantly we looked at chute density in biomass and to a lesser extent, error extent. And we have the dependencies there with factors relating to recovery, to resistance, the environment itself. And these are time varying factors, as well as location. So whether it's shallow water, deeper water, tropical or temperate, and so on, genera and time of year. But of course, these rounded rectangular boxes are subnetworks. So for example, for recovery, we have the processes, the pathways relating to growth, so lateral growth from existing individuals and immigrant fragments, and recovery related to seed, so seed density, quality, as well as immigrant seed, and these affect their ability to recover. On the resistance side, we have the physiological status of the plants, how healthy they are, and there are measures for that related to amount of rhizome carbohydrates and the like. These blue bubbles relate to the environmental factors such as light, burial by sediment, and sediment quality. Okay, so that's just a very rough overview of the sum of parts of the DBN. And so where the challenges arise are from some of the feedback loops, capturing some of the processes. And the reason why we need non-homogeneous modeling is because there are two regimes, basically. Well, actually more than two, but the two I'll give example of is, for example, in a recovery regime, you have more seagrass that produce more seeds as a result of all the different plants. There's more recruitment from seeds, greater recovery, and hence you can have more seagrass to a certain extent. And then there are rules for as you reach saturation, you stop. But that can switch to a loss regime. So when you're losing seagrass, that results in less seed production, which means the next season there's less recruitment from seeds, less recovery, and then less seagrass. So to be able to switch between these two regimes is critical. So this leads us to the idea of path dependency versus no path dependency. So in a path dependent system, which needs a non-homogeneous DBN, we are able to capture this switching between regimes, basically changing the conditional probability tables behind some of these networks. And that means so what we're looking at here, on the x-axis, we've got time from 2015, 16, all the way to 2020. On the y-axis, on the top parts, we have the marginal state probabilities for high, moderate, low, and zero shoot density. I'll go into this a little bit later on, but to make visualization a little bit easier, let's look at the weighted mean plot on the bottom. So on the left, if we have a model that can take into account path dependency, what happens is in 2016, we're simulating a disturbance that leads to a loss in shoot density, but then the model can switch between a loss regime and then a recovery regime, and then correctly capture the recovery in shoot density. Whereas if our model is not able to capture path dependency, then we suffer a loss due to a disturbance, as you see on the right-hand side, but then we do not correctly switch into the recovery regime afterwards. So that means then we have to go about, well, how do we incorporate and do inference with non-homogeneous DBNs? So a common way to do inference for DBNs is simply to unroll it, to convert it into the equivalent BN and do inference. And as you know, there are many, many ways to do this. Just bear with me, I know everybody knows this very well here. So we're interested in the posterior probability of some known X given the evidence. And we find that out, of course, by multiplying all the CPTs, or the conditional probabilities, P of X given its parents, incorporating evidence, hard or virtual, in this formulation. Each time we have to multiply, we add a node, we have to multiply by its Markov family, but not multiplying nodes that have already been multiplied, marginalize out every other node except for the node that you're interested in. And to evaluate this, we can do different approaches such as bucket elimination. Probably the most popular would be message passing a la clustering by Lauritsen et al., which is again based on marginalization and multiplication. And there are many ways to do this. There are also approximate methods. But here, our basic idea is that for many complex systems, they're characterized by small world networks. So basically, most nodes in the network only have a few neighbors, only a few connections. But there are a small number, a couple of nodes that have many, many connections, many, many parents or many, many child nodes. So the idea is we can classify these nodes as linked nodes, the small number of nodes that connect many other nodes, and we use these to do inference in a computationally efficient way. So what does this look like? So in the bottom here, we're just illustrating a standard DBN, simple example, time slice 1, 2, 3, and so on. We've got our nodes A, B, C, And here, C is our link node. It has the most connections, and it's the one that joins to the next time slice. And we denote our link nodes as this pi of t within each slice. I won't be able to go into all the details of this, but suffice to say that if the nodes that link between time slices do not have the most connections, we could redefine, because these are template models, our slices and have an offset so that we are able to satisfy this definition. And the basic idea behind this is, okay, once we've got linked nodes, we're able to do pre-computation, forwards and backwards, that's PF and PB, to calculate these partial results. And then we're able to do updating of the CPTs in a non-homogeneous sense, and then to calculate the posterior marginals for every node in every slice. So what's happening here in the forward? So that's this part here. So we start with t equals 1, 2, 3, and so on. What is happening is we're finding the partial result of the probability of the link nodes given the evidence. So basically multiply, marginalize A and B here. And then here's the backwards. So this is starting from capital T, the end time, and going backwards. Okay. So, oops, sorry about that. Q1, of course, just the first time slice, and QT is the last time. So it's this idea of doing partial results for forwards and backwards using allowed by link nodes. And then once we have our PF and PB, let's say if we're interested in time slice 2, we can then do our standard multiply and marginalize to work out the posterior marginal probabilities for any of our nodes in time slice 2. And you can do that for any time slice. Okay. So how do we then do non-homogeneous inference? So as we saw before, we can step through the network. So in this simple dynamic forward inference, what we do is we start with time slice 1, 2, 3, and so on and so forth. We can compute the marginals at time slice t, given PFPB, like we have shown before. And we use those results to update the model at the next time slice, t+1 and t+1. Then we, of course, update. So this would be for PF, right? The forward chain. And then we just repeat. So basically, in the simplest case, we can interleave both the pre-computation step and the computation of marginals. But if we wanted to take into account non-homogeneous updates for forwards and backwards, this is where things get tricky. So in general, you cannot guarantee convergence. So this is one way to get an approximate solution. Notice here, we're separated now. The pre-computation step is separate from the computation of the marginals. Because in the pre-computation step, we already do updating of the conditional probabilities. This is in the forward step. This is for the backward. So in our pre-computation of PF and PB. And then in our main loop, we again iterate through t equals 1, t equals 2, t equals 3, all the way to capital T, and again update the CPTs given those pre-computed results. And happy to talk about this separately after the talk too. What does this mean? Okay, so here, what are we looking at? We're looking at here the states for shoot density, high, moderate, low, and zero, and their probabilities. And these map to regulatory requirements for a moderate level of protection. And on the bottom, we're looking at one of the key environmental drivers, which is light. So yellow is close to probability of 1 of being good light, basically having saturating irradiance. And then red is having almost probability of 0 of saturating irradiance. So this is for Northern Hemisphere. We start with July in summer. And as we step through, we input our evidence, we can simulate and look at as we go into winter, the probability of 0 shoot density increases. And so it's transitioning from high and moderate states to low and 0. But then as we go into spring, we see recovery and the probabilities return to the high moderate states. However, the whole point of a complex system is that we're modeling many different nodes and their relationships over time, right? To try to interrogate it and find out why some things happen. So here we're looking at, for simplicity, we're showing the weighted means for shoot density, loss, recovery, and the physiological status of plants and the light. So as we might expect, in summer, we have good shoot density, good physiological status, but as we get into poorer light, the physiological status declines, which drives loss in shoot density, and then that results in loss in the actual shoot density, the realized shoot density. But as we go into spring, the physiological status recovers, the loss decreases, the rate of recovery increases. It also coincides with recruitment periods during the season. And then finally, our realized shoot density recovers. So what? With this kind of model, which we cross-validated, developed using a combination of expert knowledge and data, and it was actually surprisingly accurate. Mean squared error on the order of like 2% to 5% for the predicted probabilities. Now we can then use this model to develop mitigation strategies for dredging. So one of the ways to do this is through timing. So on the columns, we've got dredging, no dredging, 1 month, 2 months, all the way to 12 months of dredging. On the rows, we have different species. So basically, we've got strong species, weak species in the middle here, and a moderate. And blue is where you satisfy resilience criteria. So we're looking at patterns over time now, not just one single point in time. So as you might expect, the strong species are resistant and then they collapse once you go past that resistance. But for other species, they are windows in time, particular times of year. So this is kind of like a clock here. With 12 is December, 6 is June. So particular slices of time, like you see, for example, here, where if you do dredging, the meadow is able to recover, but at other times it doesn't. So what we found was ecological windows. So this was based off a global study, can enable up to fourfold, so 400% reduction in recovery time and 35% reduction in extinction risk. So, and this is made possible by our non-homogeneous DBN. So that brings me to the end of my presentations. Happy to take any questions. Thank you.
Thank you, Paul. Fascinating. Kate, are there any questions?
Yeah, we've got one question from Thang. It's how to implement this Precision Bayesian network algorithm in software such as Genie, Netica, R, and Hugin.
Excellent question. So this was a lot of coding, basically. So version 1 of the software I wrote in R, and this is up on GitHub as well. Version 2 is in C++, so to be faster computation. And currently we have interest in to combine these kinds of algorithms with MCs and basically learning Bayesian networks. So we're looking at a GPU-based implementation. So yeah, definitely going beyond what is currently offered in Genie, Netica, R, and Hugin.
And is your tool available for community or still at the research phase?
There's some that is available on GitHub, and I'm happy to share the link later. But yeah, it is still research software. But happy to talk more if there's any way this could be used.
Yeah, thank you very much. Great work.
Thank you.
Yeah.
I guess I had a quick question. So some of the link nodes, so you're mentioning that, you know, the link nodes are basically on the small world kind of approach. How small?
That's an excellent question, and that's probably an area for future investigation, actually, because of course, if you think about the pathological example of a mesh network, where every node has the same number of neighbors, then that's not particularly suited to this particular approach. So it's certainly areas for future research, I think. As you go to non-homogeneous inference, so in our example, right, in our method, we look at only updating of CPTs, of conditional probabilities. So no change to the graph structure. And Grizzly Gore check it out. They also found this because with too many degrees of freedom, that actually worsened their cross-validation results. But it's certainly an area of, it started off very, very niche, but it's growing. There's more and more use of these non-homogeneous deviants, but then also a need for better and better methods.
Oh, definitely, yeah.
Thank you. Thanks very much, Paul, and thanks for the questions. And I think we can move on to our next speaker, who probably doesn't need any introduction, but I'm going to introduce her anyway. So Anne is one of one of the founders of the ABNMS Society, and her engagement with this society has been continuous since 2009, I think. She's the interim dean in the Faculty of Information Technology at Monash University. She specializes in the broad area of artificial intelligence, and she's a leading international researcher in Bayesian networks. She has applied BN's modeling in a variety of domains: epidemiology, medicine, education, environmental science, only to name a few. And she's gonna tell us today about BARD, which is an online tool to support groups collaboratively build BNs. And whenever you're ready, please share your slides and tell us.
You're on.
Yeah, I got it. The phrase of 2020. Have I shared the right screen, not my presenter view, but the full screen?
Yep, that's good.
Yep, it's good.
All right. So those of you who were at ABNS a couple of years ago will have heard a version of this talk. So the BARD tool arose from an IARPA funded project where we wanted to help do Bayesian network elicitation by groups. And originally it was intended particularly for intelligence analysts who weren't BN experts. But subsequent to the project finishing at the end of 2018, we've been sort of transitioning BARD into a more general purpose tool for group elicitation. And so that's what I'll talk about today. I have got on this slide the overview paper, which is now under review, but there's an archive version available that gives a sort of a summary of the BARD method and the tool. And also just wanted to give a quick advertisement for the workshop that I'm running tomorrow, which is supposed to be a hands-on workshop. So if anything I say today captures your interest, do feel free to sign up for that. We've got plenty of spaces for people, even if you haven't registered already. So I'm going to really just touch on a few elements of BARD. So I think I don't have to persuade this community why causal Bayes nets are good for a good modeling technique for representing an argument, representing uncertainty, representing reliability of sources, and so on. In particular, we do elicitation when there isn't the data available to drive the learning of the models. And apart from experts, of course, often experts bring in information from a variety of sources. What I would say, just as to highlight some of the differences from people who heard the talk 2 years ago, is that we've now extended the BARD tool to handle decision networks, so it's decision and utility nodes. And also we've got a bit more integration with some other tools, and then you can upload, for example, a Netica network, and you don't have to start from scratch in BARD, so you can integrate using it with other tools. And we've also started to integrate with some of the learning capabilities. So now you can actually learn the CPTs from data, even if you've elicited the structure, for example. So the idea of the groups in BARD is a Delphi style group. Now, I'll talk about Delphi in a minute, but the idea is that you'll have a facilitator and then you'll have a certain number, we would call them analysts, or they're just the people or the experts who are there building the group. We divide the process up into stages. I'm going to talk today about building the Bayesian decision network iteratively and incrementally. There's a kind of a pre and post stages that are supported within BART as well, but I'm not really going to talk about those today. So all of you now are familiar with building Bayes nets, and you've used probably Netica or Genie or one of the other tools. Some of you may have done some programming as well, but all of those tools would have the GUI interface. They kind of assume you know what to do next when you're building your BN. They assume that you know an order of process about putting the variables together and then adding the arcs and parameterizing and so on. But what BARD does is it actually turns it into a structured workflow, and I'm talking here in particular about these steps 2 to 5, where the tool itself, which is online web interface, has different steps and different screens that you do to do each of these different stages, and it's really explicit that you move through them, of course, in the natural order from variable structure through to parameterizing, and then what we call exploring the model, which is doing the reasoning. And these arrows here really reflect that you move backwards and forwards between those steps naturally when you're building your BN. You know, you might start with a certain number of variables and connect them up with arcs, and then you might realize that you've missed something. So you add another variable, or then you might realize that there's some arcs that you need to change. And so that's what we mean by iterative and incremental. So just to show you here, I'm not going to talk about the details of the software now, but what I wanted to point out is here across the top is tabs, if you like. So when you click on each one of those, you get a different screen up here, and they're numbered, and these are the steps of BARD. So you can basically move backwards and forwards between them. There's some limitations the first time you go through. I mean, you can't add structure until you've got some variables, but then after that, you can move backwards and forwards by clicking on these and moving in between them. So that's what we mean by a structured process, because it's clear what the order is, and you see different things, and you have different options available to you in each of those stages. Now, in terms of the Delphi style, I don't want to talk too much about Delphi methods, but they date back to the 50s. It's about group decision making. The idea is to have certain features, for example, expert or analyst anonymity, to remove bias and influence, to go work via a facilitator or moderator. And there's many versions of Delphi. And when we were building BARD with the idea of being inspired by Delphi, we played around with a lot of versions of Delphi. And in the end, we came up with a fairly flexible, only Delphi-like process. In fact, Delphi purists don't think that our method is very much of a Delphi method, but certainly inspired by some of those aspects of Delphi. So you can move between you can do your work and do the elicitation asynchronously. That means that people don't have to be logged on at the same time. And we know that's one of the problems sometimes of getting experts together and having them available all at the same time. So people can come in when they've got time and do some work and contribute to discussion forums or whatever it might be, and then leave and come back later. So they don't have to be at the same time. There's anonymity unless you actually want to put, you can remove that and give someone a meaningful name, but by default it's anonymous. The idea is, though, in which what we have kept from Delphi is that there's a private round, just where you have to do something first yourself, like give an opinion or create a variable or put some parameters and whatever you're up to. You have to do it yourself first before you can see what other people have done. And that's the idea, that you're not being influenced by what you've seen other people do first. Now, later on, of course, there's interactions between people and they see what others have done and then they change. So we have a structured process where you see what other people have published using discussion forums. Now, what we have is that the facilitator can actually produce a version as well, which is the group version, which publishes when ready, and the analysts or the experts can see that group solution once they've done, again, their own work. So So this is a very formal description of that interaction between what the analyst does and what the facilitator does, and how certain things happen at certain stages in this interaction. So the details aren't important, but I guess the idea is that there's some structure into those interactions. And in particular, you have to publish before you can view other analysts' work and before you can view the group response. So the way that that's captured in the network, I already showed you before the 6 steps of BART across the top. Then for each of those steps, there's the My Draft, which is where you work on your own version. Once you've published it, then you can go and see with a drop-down menu everyone else's published work. The group is where you see what the facilitator is put in, if anything, about that consensus solution. And there's a discussion forum. Now, I'm just picking up on something that Dennis said, where he talked about the need to provide a narrative around the elicitation process that's important for the sort of the clients or the stakeholders. What we found is that that discussion forum does document that reasoning and the discussions that are being held during that elicitation process, and forms that narrative. Just wanted to point out a few aspects of BARD, not too much detail. Pretty clunky interface, and we want to fix this up. But basically, when you put in your variables, you can distinguish where something's a target variable, which is the one that may be the intended sort of output, if you like, of the network. But you can change the variable, and it really just shows up in different colors and so on in the visualization of the network. You can change that, but now we've added decision and utility nodes, and this load network from file in the bottom right corner shows that new functionality from loading up, and that we found that can be quite helpful. In fact, you can do things like load up just variables if you want all your people to start off with the same set of variables instead of have to type them all in and get that consensus, and then they can start talking about, for example, the structure and other aspects, and don't have to do the elicitation on the variables. But or you can just load up a starting network and then get people to discuss it and then change it. In terms of the structure, we actually have a pretty cool interface, because it lets you zoom in and zoom out and pan, and there's some automatic graph layout in there, and you can enforce certain styles of layout if you want, using constraints. In terms of the parameters, we have ability to ask elicit them via questions, which is an example here, where the questions around the conditioning case from the parents, and how likely is it that this is the numbers that you need to elicit. So here it's numbers in a question format. Here's an example where it's a table format, and here the answers are in those verbal descriptors, and you can have any combination of those. One thing I wanted to highlight, which is new, is this is where the learn parameters from the CPTs here. We've also added in an ability to specify nausea, or nothing like the sophistication that Marek told us about his new availability in Genie, but all of those things in future could be added. The Explore network is really where you, as you're building a BaseNet, often you want to, especially once you've done some initial parameterization, you do want to see what's happening with the network and what it does under particular scenarios. So you can enter scenarios and save them here, a bit like that's like a GINA risk kind of notion of a scenario. We use that. You see it in the middle. You build your own scenarios and you see the outputs over here. It would be nicer if they were sitting on the actual canvas, but we haven't done that yet. But we can also add likelihood evidence, and we've got this automated explanation. If you'll see down here, this is automatically generated text that talks about the scenario and the reasoning and puts it in English language. And we also have a detailed explanation which talks more about the structure of the network, the causal structure, and so on. So that's automatically generated. Our tool uses, at the moment it's set up, if you do the workshop tomorrow, it'll be using Netica as the back end. We have, during the original project, we linked it into a GINA, and it could be replaced by anyone. So if you've got some other favorite BN tool and you would like to integrate it with it, if you want to persuade the software developers of that to provide us some resources to integrate their tool, that would be great. Now the project's no longer being funded. We're limited unless we get some funding to do that. and you can download the BN output, of course, and then use it in your other favorite tool after you've done the elicitation in BARD. I'm just mindful of the time. How long have I got? A couple of minutes?
Couple of minutes, yeah.
So I won't talk too much about this detailed explanation, but it's quite long. Describes the causal structure, reliability and bias. What we're actually working on now, we've got a funded ARC project to look at multimodal and interactive explanations as part of that exploration of the network. We've been a bit delayed due to COVID and hiring, but our newly appointed research fellow Penny Zhang's attending ABNMS now and getting up to speed with BARD and BNs. So we hope to have progress on that soon. I've got a lot of training available and there's a lot of help embedded because we're really pitching BARD at people who haven't used BNs before. You know, if you're recruiting experts and you want to use it, you can select some of our training to show them beforehand so that they've got some familiarity with it, and then you can focus on the elicitation itself. I did want to say that we're finally getting some papers out from the project. Our main methods paper, which I already referred to before, is under review, but we've got an archive preprint available, and we've got 2 papers that describe a couple of our experiments we did during the project, one using BARD in groups. And we actually have a version of BARD that isn't the group version. We just basically turn off all the groups and just let you use it for a structured building of BN by one person. So we call that solo BARD. And we've had experiments done showing how solo BARD, what it does with reasoning compared with people not using a BN at all. If you are interested in using BARD, again, tomorrow's workshop, you'll be welcome. I'll give a demo of those features sort of live and then put people into groups to work on building the BN. And if you join that, I'll give participants a demo account with access to the training, which we'll leave open for a couple of months. And we're really keen to build research collaborations with anyone interested in using BARD for any kinds of reasoning and decision making, of course. And one last advertising, completely nothing to do with BARD, but we are interested in how people understand intuitively the reasoning of BNs. So with, led by Morva Ed, one of my colleagues at Monash, we're running an experimental study where we want to get people in and tell us what they think the answer to some scenario where they're shown a BN is. So you have to know something about BNs, but we don't want you to do the BN computation. We want to get an idea of your intuition about what you expect the answer to be. And that's going to give us an idea of how to provide better explanations and better visualization, because the idea, if we see where people are struggling to understand intuitively the BN reasoning, we'll do better with our design of our interfaces and our explanations. So I'll put the link on that in the later. Okay, I'm going to stop now.
Thanks, Anne. Are there any questions?
Yes, we've just got one from Helen. It says, "Hi Anne, looks fantastic and very helpful. Does every participant need to publish for every answer? For example, in an interdisciplinary model, can some experts just publish the answers to the areas they are experts in and skip other sections or nodes?"
I'm trying to stop sharing. Okay. So it's a bit tricky. One of the things you can do is divide the problem up into smaller parts and have different people eliciting different parts of the model and then integrate it later. The other one is that even when we're in it, even though we say that people have to publish something, if people really are not sure or don't have enough knowledge about it, they can basically publish nearly an empty model. That effectively means if they don't know enough about whatever's been discussed, they can kind of skip it. So yeah, we don't enforce a certain level of new material in whatever you publish to move on and see what other people do.
So there is kind of like a workaround to it where you can just put a dot and hit publish.
Exactly. You can put a variable called X in and publish it and then have a look at everyone else's variables.
Okay, cool. Excellent. Thank you.
That's why people say, is this really Delphi? You know, if people can kind of, but on the other hand, because it's asynchronous and people are used to online tools actually being able to do quite a lot, people don't like being really constrained and being kind of told you have to do this before you're allowed to do that. So it just gives that kind of some structure, but yeah, there's workarounds.
Oh, there's always someone who'll go rogue, so.
Any other questions?
There's no other questions in the chat at the moment.
I look forward to
I have a question.
Oh, yep, sorry, yep.
Quick one. So in the interface, it looks like you have to set up your variables and then you go to the structure. Do you have to say what type of variables you're working with before setting the structure? Do you have to choose that they're discrete or they're continuous or whatever it is that you can choose?
There's a default when you create a variable. I think it defaults to true false, and then you can go back and change it later. And the only implication is if you've put parameters in and then you change it from a 2 to a 3 state 1, for example, then you can lose your parameters. Yeah.
Thank you. Okay, thanks, Anne. Thanks very much. And we'll move on. And our next speaker is a distinguished professor of statistics and director of the Center for Data Science at QUT in Brisbane, Australia. She is an elected fellow of the Australian Academy of Science and also of the Academy of Social Sciences of Australia. Kerry's area of research interest is in Bayesian statistics and modeling of complex systems, including Bayesian networks with applications in health, environment, and industry. And Kerry will speak today about combining expert elicited judgments for BNs. Whenever you're ready, Kerry.
Okay, thank you very much. Thank you for the opportunity to speak at this meeting. It's very exciting and it's so interesting hearing from previous speakers. And Anne's work is amazing, and thinking of, you know, instead of us talking about the Delphi method, soon we'll be talking about the Nicholson method, and it'll be very exciting. So I'm going to share my screen to present today on the topic of combining expert elicited information. So just let me know when you can see my full screen. Can you see this?
Yeah, works fine.
Okay, great. So I want to talk about combining expert elicited judgments for Bayesian networks. And I know that there are many people in this meeting who know a lot about this. So I'd be very interested in your comments, both within the conference and also externally. So this is work in collaboration with a large number of co-authors over the years, and in particular for this talk with Paul Wu, Sandra Johnson, who's talking next, Samalo Choi, who many of you know very well, and Fabrizio Ruggieri, who is a collaborator from Italy. And so what I want to also acknowledge first is the support of our Centre of Excellence in Mathematical and Statistical Frontiers, and also our new Centre for Data Science, which includes the Data Science at QUT network, and also the Australian Data Science Network, which links different centres in data science around Australia. So I want to talk about complex systems, complicated systems, and of course we know all about these. We've heard from Paul about the seagrass systems and dynamic Bayesian networks as a natural fit there. Sandra and I have worked on biosecurity problems across the different countries in Southeast Asia and also in Western Australia, and also on conservation problems such as cheetahs in Southern Africa, and I'm sure some of you have heard Sandra talk about that in the past. And we've also worked on Bayesian networks in health, different aspects of health and epidemiology, and of course Anne's work with COVID-19 in this aspect as well. And so one of the other areas, of course, is in airports. And once upon a time, it will become a bedtime story. Once upon a time, we used to travel in planes and around airports. And we used to have these big airports where it was difficult to find our way. I know this is hard to imagine now, but there were lots of people crammed into small places once upon a time, and it was difficult to find your way around. And so when we think about wayfinding, this is also a complex model or complex system, and we can think about all the aspects that are involved in wayfinding. And so a PhD student here, Charis Farr, did a lot of work in collaboration with a number of airports, including Brisbane Airport, around what are the factors involved in wayfinding, and created this Bayesian network, quantified it based on the judgments of a number of experts and also the opinions of a number of travellers. So if you don't know what the word traveller means, then you can look at an old dictionary. You might need to get the paper copies out. But once upon a time, there was a word called that too. So we have here you can see environmental factors and human factors as the main drivers, and the sort of the main nodes. And from those, then a large number of factors that feed into the human and physical and environmental factors that you can see there. So, so if we think about quantifying this kind of network, then we're all familiar with the kind of structure of a Bayesian network and how we might quantify this using CPTs, conditional probability tables. We can also have continuous variables and continuous distributions. Now, this is fine when we just have one expert, but of course, if we have multiple experts, then the question becomes, how do we actually quantify that? And so when we think about that, then a common approach to doing that is some sort of linear pooling. So the information about a particular node provided by a number of experts is going to be thought about as a joint model of probability of that particular node given the experts, and we combine that. We can combine that through a form of just linear pooling where the lambda I here is a weighting for each of the experts. And if they're all equally weighted, then we're just going to have pretty much the average of the probability provided in that node. Now that's fine, except, and we can do it in two ways. We can have prior linear pooling, where we have the pooling applied to each node, and then we propagate the resultant CPTs through the network to find the marginal probabilities for the nodes of interest. And the other way is to run each person's Bayesian network, run the probabilities through that particular Bayesian network, and quantify and compute the marginal probabilities distributions for the final nodes in the NBN. So we have just the final nodes then from each of the experts, and we combine those. So that's fine, except there's some drawbacks. But the main ones are that we have the point estimate for the consensus at each of the nodes if we're doing it through the prior linear pooling, and the variation in the expert opinions is lost at each node. And if we do that, then of course we don't have this coherent probability model because we actually have correlation between an expert's judgment at each of the nodes, and we would lose that connection for an expert across the nodes if we do this prior pooling approach. So, and if we do prior pooling and posterior pooling, then we can show that we get quite different outcomes for the different nodes of interest. And the conditional independence structure of the BN is not reflected in the way that we do this prior linear pooling. Similarly, for the posterior linear pooling, we lose the variation that's associated with the variation in the different nodes when we come to the posterior estimates. So one other approach that we can look at is a measurement error approach. And so this has been tackled in the literature in a number of ways. And this is the approach that I'd like to talk about that we published this year with the authors that I said, Charis's work, and with Fabrizio and Paul. So considering a single node of interest, then we have the marginal probability for an expert I. And if we think of it as just a two-state CPT, this can be extended to multiple states if we have, or multiple categories, by taking the beta and making it into a Dirichlet. But if we think of it as just as two states in a single case, then we'd have PI, the probability for that particular node is going to be expressed as a beta distribution, where the AI and the BI are going to tell us about the point estimate, the expected value, and also the variation in that response. And so we can allow then for variation between experts if we take that PI and we actually have put it on a logit scale. So now we have the logit of the expected value of PI is going to be the logit of AI on BI plus an overall value. So there's going to be some overall probability plus some deviation for each of the experts, plus then some residual expressed through the epsilon I. So now we can have the mu-I, which is the overall probability, is going to have this prior distribution, and then we have just the a normal distribution for our residuals. So now we're in the sort of the world of having this random effect for each of the experts, with some overall mu that we might be interested in as some combined effect. So one way that we can model this through some assumptions in this is saying that AI plus BI has a gamma distribution. And so what we're interested in is the parameters of the gamma distribution, alpha naught and beta naught, which will tell us about this overall probability. So we can go from that, from a single case, to now we have the consensus for multiple nodes. So now we move to a multivariate situation where we have PI, J, where the J defines the multiple nodes. So now we have a multivariate normal random effect for each expert, plus some extra between expert variation. And so this is just the expansion of that univariate case that we saw before into a multivariate case. So this is now going to encompass the whole network, if you like, all of the nodes of the network, and the correlation between the nodes is going to be encompassed through the covariance structures, the covariance matrices in the mu and in the epsilon. So if we have a look at that, then the structure of this random effect term is going to have this matrix structure, which is going to incorporate this correlation between the different nodes. And so this is how we're going to encompass the variation between the experts and the relationship between the different nodes. And so it's all comes down to this R, if you like. So this is the way that we can characterize this precision matrix Q in terms of R times R transpose. And so if R has the correct sparsity, then Q will also have the correct sparsity. And what I mean by that is we know that not all of the nodes in a network are connected. So this R is going to actually reflect the way that the nodes are connected. And so the sparsity is when there's two nodes that are not connected in the network, then that term is going to be 0. And so it really reduces then the computation, because we don't have a full matrix. A lot of the terms in R will be 0. And so we can actually represent our equations in this way. And by finding this R, then we can give Q the right structure to reflect the conditional independence of the BN. So this is going to encompass the information that we want from the different experts, the variation between the experts within each of their BNs and also across the nodes, but also make it sparse. So we just can have zeros or empty space where we don't have any of the nodes connected in the network. So if we go through this approach, then this is actually a great improvement on the usual approach of linear pooling. So just as a simple example, if we take that wayfinding case and we just have two nodes, human factors and environmental factors, so just the two main ones, we can see that because of the structure of the network, then we actually only have the combinations, only some of the combinations in Q are actually non-zero because of the structure of the network. So we can have, for example, in this case, 99 networks. The model allows for a combination of all opinions. We have coherence because under the reordering of the independent expert opinions. And this Q allows us to borrow strength from the other parts of the model. So the information can travel up and down the different levels of hierarchy. And it also ensures that the conditional independence structure of the BN is reflected when we're combining these opinions. So I'm not going to go into the detail of this, but I've got it in the slides if anybody would like it. And of course, it's more explained more in the paper. So we need to construct R, and we can write it in different ways with respect to these overall probabilities for each of the nodes of interest. We have here the H, the E, and the W, which is going to refer to the human factors, the environmental factors, and the overall wayfinding. So you can see, for example, the overall wayfinding, the third equation there, is going to have some overall value for wayfinding plus something that's related to the human factors plus something that's related to the environmental factors plus then some residual related to the wayfinding as well. So you can see how they're all building on each other depending on the structure of the network. And so again, we can build this and we can put priors on these different parameters in the model. Usually we use some sort of uninformative priors so that we can let the data talk, especially when we have a larger number of experts. We can do this analysis in R-INLA. So this is just some details if you're interested in this, but we have the code and are happy to share that. So this is a faster, more accurate alternative to simulation-based MCMC in many cases. So the kinds of results we get are posterior distributions then for the probabilities of interest, and these posterior distributions will reflect the variation across the different experts. How am I going for time?
Another couple of minutes.
Okay, all right. So this is a new measurement error approach for combining opinions in Bayesian networks, and the results can indicate improved performance and increased inferential capability compared with previous approaches. We can also extend the model to include bias and additional covariates, for example, experienced and inexperienced travellers, and we do that by modifying the Q, the overall mean. Now, I'm going to skip through a couple of slides, but I do want to touch on just two other topics. One is when we want to combine expert opinion at scale. And in this particular case, we're looking at annotating reefs. Now, this hasn't been implemented in a Bayesian network context yet, but I would like people's opinion about this, because the case we have here is that we have a lot of citizens who are annotating images, and now we want to look at the credibility of those citizens. So we want to understand the ability, the latent ability of each of these people who are annotating images for our virtual reef diver project. And I'm happy to talk a bit more about that if you're interested, or you can Google virtual reef diver. Now, again, this is not a Bayesian network, but the reason I'm saying this is because we actually have thousands of participants who have contributed to this. And in fact, hundreds of thousands of participants can contribute to crowdsourcing projects via Mechanical Turk and other citizen science platforms. And the ideas that we've developed here to look at the innate or the latent ability of our experts might be interesting in a BN context. And so here we can look at estimating the ability of each of the people by, if you just stare at this equation, I'm just going to show you, it has a term in this for the latent ability of the user accounting for the difficulty of the image. So if we translated this to a BN approach, we would be looking at the latent ability of our expert taking into account the difficulty of the node. And we can even relate the nodes. The last equation there is saying that in this case, the images are related to having the spatial arrangement. So they're related to the neighbors. So we could think about this in terms of a BN where we have each of the nodes, the difficulty of a node, even related to the difficulty of the associated nodes, where we have these kinds of Markov blankets or sort of different functional aspects of a system. So just thinking about how we might translate this so we can get an estimated ability for each of our experts. Now, another way that we might be able to get estimated ability of an expert is to actually build an expert Bayesian network. So we don't really have an idea of what our experts are or an expertise means. And so we really want a system approach to that so we can think about a BN. So we did some work with Julian Cayley and Paul and others here. And if you just look at this, we have a way of being able to do this, but we actually put together a Bayesian network on the features that were important for a taxonomic expert in this case. And then we quantified that to understand like what were the most important aspects of an expert. And you could imagine then at the end of this, we could get for each expert, adding their information into something like this would then tell us about the overall probability of that person being an expert, which might be considered as a score or a weighting in an expert evaluation, and then also in the BN. So that could come into the first slide when I talked about, well, we want to be able to weight our combinations of the expert opinions. So this model then has an interesting idea about how we might come up with a definition of an expert. So overall then we have combining expert opinion should take account of the full set of information provided by each individual. We can estimate an expert's latent ability, taking into account the difficulty of the nodes in a BN context, and this could help to weight the information provided by each expert. And we could also consider what we mean by an expert and then perhaps weight accordingly. And here are some references, and I'll leave it at that. Thank you very much.
Thanks, Kerry. I have a million questions, but before that, Kate?
There's just one in the chat so far from Heng. So did you want to ask that directly, Heng? It's about...
Yes, I can. Hi, Kerry. Thank you very much. That is excellent one. Combine expert and allow the uncertainty in there. So way out thinking about that problem, and so it. I want to start the first question first. Probably it's a kind of this more technical question. We tend to ask in statistics when you do composure error measurement, you use IED, the normal distribution. Is there that why that limitation and why have to use? Is there any way to overcome that?
Yeah, so you're right. We've assumed here that each of the experts is independent. We have the dependence for each expert, the dependency that exists between the way that they have quantified each of the nodes is encapsulated in the model, in that queue. But in terms of the experts, at the moment, we've considered them all to be independent. But you're right, perhaps they're not. Perhaps there's actually like subgroups of experts or some ways that we think about experts coming from different research groups or some ways. So we could actually think about building that as a hierarchical model now. So we can think about experts within a subgroup, and then we have the subgroup means actually being combined at a top level for within the construct. So now you can imagine that matrix, instead of just being a single matrix, which would then involve for each expert and each node, we would actually have an enlarged matrix where we would have subgroups of networks, and then we would have, independence between those groups or characterized dependence. So I could see a way that you could build that up using the sort of the hierarchical models that we use in mixed models or Bayesian networks. Oh, sorry, Bayesian hierarchical models.
Oh yeah, thank you very much. It's suitable for our problem domains because we work with defense, so they're very hierarchical. So always got the group and the different
Right.
ones.
Okay. Yeah, that's right. Yeah. So you could certainly incorporate the correlation structure between the experts, which would be interesting to see, because I think it would be interesting to see what where most of the variation is coming from, or how sensitive the models are or the responses are to that kind of collusion. In a positive collusion.
Yeah, hope so. Thank you.
Thank you. I think in the interest of time, we have to move on to our next speaker. And that's Dr. Sandra Johnson. And Sandra is an ABNMS board member, and she was one on and off for many, many years. She's now a researcher at Consensus. I'm hoping I'm saying that right. But she started her career as a software developer at IBM. She worked at the University of Queensland as an environmental statistical researcher and at Flight Centre as a senior data scientist. She is also a visiting fellow at the Australian Research Council Centre of Excellence for Mathematical and Statistical Frontiers. And her talk today will be on the role and challenges of expert elicitation in blockchain technology. Sandra, whenever you're ready.
Thank you, Anka. I'll just try and share my screen, making sure I share the right one. Desktop one. Can you all see my screen that says the role and challenges of presentation? Great. Well, thanks for the introduction, Anke, and thanks everyone for staying for the last presentation. So I started working with BNs about 12 years ago. I was very fortunate to have Kerry as my supervisor. And initially, my experiences with expert elicitation were all really around working with vulnerable species like cheetah that Kerry mentioned earlier. So what I wanted to do today is just to share a little bit of these two different worlds as I've encountered doing expert elicitation in quite a different environment within the blockchain community. So basically just to introduce it, and I'm not sure how many people are that familiar with the blockchain community, but I'll just assume zero knowledge, so please forgive me if I tell you what you already know. But the blockchain world is pretty much comprised of people who are working remote 100% of the time. So we were one of those people, groups of people who, when COVID struck, nothing changed for us. Life just carried on as normal. When I first joined the consensus, they work primarily on the Ethereum blockchain. I was pleasantly surprised to find that it was actually quite a fairly diverse community within both age and background. However, the predominant group clearly would be software engineers. And it's a very active open source community. People are very passionate about doing everything open source. And it's we're certainly at the forefront of new technology, which means inevitably a very changing and volatile environment. There's a constant flow of new ideas that are being discussed and developed. Now, typically what people do is what they would set up a test network so that they can run experiments for data gathering and analysis to sort of look at these new concepts and implications, or they'll have simulations to mimic testing in a development environment. They're probably a lot more comfortable with machine learning techniques, including reinforcement and deep learning. But I found hardly any probabilistic modeling, and actually a fair bit of pushback on probabilistic modeling. Now, communication within the blockchain world is primarily Zoom. So, and I think everyone now is an expert in Zoom anyway, but that is the main way of asynchronous communication. Most of the rest of the time is asynchronously. So this little icon here is Discord, and that's where the Ethereum community are very active. So you've got different sort of channels where people would interact and talk about specific subjects that they contribute to and that they're proposing new ideas for. So the other thing is Slack, and I think a Slack message has just popped up there from work. And that is the main way that we communicate with each other is via Slack. So Slack channels, and I think quite a few of us are familiar with that. Telegram is the other one down the bottom right, and the Ethereum community were typically first busy there and then migrated a lot of the discussions onto Discord, but there's still a lot of people hanging around Telegram. And then there are other communications things like Gitter, and in GitHub, people, when they set up a GitHub repo, they'll raise issues and that will then prompt further discussion and investigation. There's also blogs, for example, notes ethereum.org. So if you do a proposal of something could be introduced within Ethereum, typically someone, even if it's still a new idea, you'd put it onto HackMD and then there'll be people engaging in those discussions. Email is a lot more not infrequent. So expert elicitation in this environment, as we know traditionally, and what I had been used to up until blockchain, was through semi-structured interviews and questions. So typically by consensus, a Delphi approach, idea protocol, and a shout out to Anke, who's running a workshop, which would be really interesting, where she will discuss the idea protocol. You've already heard from Anne, who's doing BARD, so there's great opportunities there to look at different expert elicitation techniques. Counting using visual age is really helpful, and that is what Trent Penman and his research group and Kate found when you're using a visual aid like a house, a little monopoly house, to give you an indication of the relative risk of the number of houses lost as to an indication of the relative fire risk. However, in all of it, I think we all would agree that face-to-face elicitation is the best. But for me, next best, certainly, as all of us had to do, would be Zoom. So the expert elicitation that I started before COVID is all happening mainly via Zoom calls. Now, Zoom fatigue is actually a phenomenon, and it's important to avoid Zoom fatigue because, like, for example, today I started at 6 a.m. and my last meeting today will finish at 6:30. That's not a normal day, but that is what happened. And sometimes I have a day that there's far too many Zoom calls. Now, the default session time is sort of 30 minutes. If you want to ask someone to join a Zoom meeting, 30 minutes, and you know that you're more likely to get people to engage. The main thing is to bear in mind is time is a precious and finite resource. So get the maximum out of your expert in the shortest possible time and be flexible with elicitation techniques. So because I was constrained with these little gaps of time, like 30 minutes at a time, I had to sort of change things a bit on the fly when I talk to my experts and have enough time to engage with them so that they're interested enough so that I can schedule another session with them. So before that, you have to sort of get your head a bit around blockchain jargon, and there's a fair bit of that around. So be able to communicate with them in the language that they understand. So a quick 10-second introduction to blockchain. It's literally what the word says. It's blocks connected by a chain, and the idea is that you can't go back historically. If you want to change a block in the past, the only way you're going to do it is you add yet another block to the chain, and that block will affect the changes that you need. So the upshot of this is that the blockchain will record changes over time and retaining all the historical information, but then the size of the chain will keep getting larger. So I'm going to talk a bit about Ethereum because that's the blockchain environment that I work in. So Ethereum, Bitcoin is the other larger one. So there's the concept of Ethereum state, which really just is the current status of all accounts and balances plus other information. So what happened is Vitalik Buterin, who's one of the co-founders of Ethereum, said we need to do something to address this unbounded state growth. And he came up with this concept that he called stateless Ethereum. And this all hinges around block witnesses. So the witness really is just providing the information necessary to execute the block so you can add it to your node that you're running in Ethereum. So the sort of challenges here is that how would these additional data packets affect the current status quo? What are the potential consequences of these additional data packets being passed around the network, and how large will they be, and can we reduce the size? So what our team proposed was looking at developing an object-oriented Bayesian network to get a holistic view of the current Ethereum network, which is Ethereum 1.0, and then capture those changes being introduced by stateless Ethereum. So we don't know enough about them and how that might influence it. So I got some mixed reactions when I proposed this. So some people, because they work in changing environment and new technologies, are happy to embrace yet something else. Other people were very skeptical. They prefer deterministic things like, running experiments. And some of them had a little bit of exposure to BN, and they had preconceived ideas which dated back a long time ago, and they, I think, had not an idea of how it could be used. So there was a fair bit of pushback. Anyway, we marched ahead and the team were all on board. And so what we did is, this is just a high level model. I'm not going to go into the model because I'm really just going to talk more about the elicitation side of this exercise. But essentially this part of the network, if you can see my cursor, is what Ethereum 1 would currently be. So we would try and find out as much information about the current state of the network and then complement it with things that we didn't yet know much about. So the witness creation and then validating your block and witness. So previously you have to only validate a block. And this then gives the model interface between those different submodels. So these are the 5 key submodels that I worked with, and I'm going to just talk about what happened there. So what we did for the quantification, and at this stage I've quantified 1 submodel and I'm busy working on the others. So it's a combination of expert knowledge and empirical data. So our company has got a database called Alethio, which has collected so much information about the Ethereum network, which is a fantastic, rich data source. There's also a lot of websites around like Ethernodes, Etherscan, and then Wonder Network, which has got ping data between cities. So they very kindly gave me a data dump. The expert knowledge, I was really lucky to be able to tap into a lot of experts. So, you know, sometimes it's a bit hard to find many experts, but I had access to the product development team who works on the Ethereum client that our company developed called Hyperledger Besu, and also the solutions team who work with clients who are building blockchain, then the R&D team, as well as Ethereum Foundation outside of our company and the wider Ethereum community. So one example that I'll just quickly talk about is the Ethereum node type. Now, I thought this was a really simple question. I just wanted to know if we simplify all the nodes of Ethereum into ones that do mining and ones that don't, what proportion of them would be mining nodes? Well, it's a very simple question, but it was surprisingly hard to answer. I posted in the end a question on Discord so that I could reach out to the Ethereum community. And as always, they were pretty quick to respond, but I got no definitive answer, even from the wider community. I certainly got into some interesting discussions offline, but it was centered about why it is complicated to get an idea of the number, the proportion of miners. So what I did is I calculated an estimate from the empirical data I had, which I knew would be over-reporting on miners because a mining node might not be active all the time, or the mining pool might have closed down, that sort of thing. So what I had was a value, and then I interviewed experts to provide an estimate of the proportion of miners that they believed were in the network. So some of them used this calculated value as their baseline or their anchor. Others preferred to just ignore it and use their judgment entirely. And others who acknowledged the uncertainty around knowing the exact number gave fairly large ranges with high uncertainty. Now the geographic, the node location, we looked at how the nodes are distributed across the world, and we then used expert knowledge to group them into regions that kind of made sense. So we ended up with 5 regions. We originally had 7, but due to the sparseness of the population, the sort of numbers of nodes, we made that down to 5. Yeah, that's it. So the reason I introduced that is that these regions then we used for peer location. So a node typically, so if you want to communicate with the rest of the network, you would have peers that you are connected to with your node. So you can either, you know, so for example, if a miner wants to say I've created this block, they would send it off to their peers, and they would then send it off to their peers, and that's how it goes through the whole network. Or if they say, I need to get information about this, then those are requests. So you basically have these nodes that are connected to peers, and there's an upper limit on the number of peers you have. So we assume that peer location depends on the type of node that it's connected to. So whether it's a miner or a mining or a non-mining node, and the location of where this node is. However, it can actually depend on other factors that is a lot more tricky to evaluate, such as connectivity and trust. So the miners would probably have direct connections with other miners so they can propagate their blocks quickly. So the distribution of this one was reliant entirely on domain knowledge. So what I did for a lot of these elicitation sessions is I put a lot of effort into the spreadsheets that I would have to talk to them. And I used that primarily as my communication and to have a consistent way to talk to everyone. So I would ask, for example, you know, what would be the proportion for a miner that they think would be in, if the miner is in Europe, what proportion of its peers would be in the other locations. So because that would probably be a bit challenging for them to do for all of them, I then suggested a couple of strategies that they could do for simplification. And also, so if they felt that the minings and the non-mining, which are called semi-status, are similar, then, you know, we can use that. Anyway.
Sorry to interrupt. If you could just wrap up.
Yep, I'm wrapping up.
Yeah, thank you.
Thank you. So all in all, what I deduced from this whole session is, as far as I'm concerned, good things come in small packages. So keep your elicitation sessions short and be flexible. Some experts find different techniques easier and more intuitive than others. So, for example, ranking relative importance of parents, much easier than providing actual probabilities. So have your bag of tricks ready and your techniques up your sleeve and ready to use. For structure ratification, beware of having too many opinions. It can take a being iterative development to a completely different level, and that's a mistake I made. Be aware of elicitation biases. Be on the lookout for people who are overconfident, and capture the conversations. I found that you can often extract important information from there. And ask your expert to talk you through their reasoning, pick up on incorrect interpretations and adjust the answers accordingly. They are more willing to, I found they were much more willing to share judgments if they were able to associate a level of uncertainty to their estimates. So saying, you know, if I think that they would typically like to just say it's this. But if they say, well, you can say how certain you are about it, then they were a lot more forthcoming in providing estimates. In general, experts have inquiring minds, and even if they're skeptical, I found that they were willing to participate. So I find working with experts always very interesting, insightful, and is a real privilege, regardless of their field of research and expertise. That's it.
Thank you, Sandra. Are there any questions? Go on.
Anne.
Oh, just on that, keeping elicitation sessions short. I'm just thinking back to a few years ago when I did more actual elicitation sessions. That people take a while to get warmed up, and I'm wondering whether if you keep them short, you sort of lose momentum, or they're just getting into it, and then, I mean, they might be losing, you know. You might be losing their concentration, but at least they're into it, and people are starting to get aligned or whatever. I'm just wondering whether you noticed that. And then when they come back, how much time does it take to get them into it again?
Yeah, well, actually, because I broke them up into smaller bits, so I would then show them the overall model. We'd have a little bit of a chat about it and ask them where are they more comfortable, you know, and I would have a pretty good idea of their specialist knowledge anyway. And then propose that I feel that they could inform this or that. So we'd have a little bit of background, so that took a bit of time. But then the actual elicitation session, if I could use my 30 minutes well enough, they'd be, the bug would catch them and they would want me to schedule another session. So that's what I did. I sort of tempted them by saying, can I have just 30 minutes, you know, have you got, can I have a quick session with you? Yep, and then they're typically always happy. 30 minutes is not too big an ask. An hour, you're pushing your luck a little bit. But I did find that subsequent ones, they were happy for me to schedule an hour. So it was almost like a little bit of a taster. And then if they think, well, this looks interesting, then they're happy to schedule a longer one. So we would recap on what they've done and whether they wanted to change anything. But I was surprised at how much we covered, to be honest.
And gap between sessions? I mean, 2 days, 2 weeks, a month, what's too long?
Oh, no, it was typically a few days. So, it might be sometimes, because when I first started, I crammed them all in the first week, and then we scheduled the follow-up ones the following week. So, yeah, there weren't big gaps between them. So I would tend to concentrate on one expert and go a bit more and finish off with them and then move on to the next. So I was lucky that in a lot of, I mean, I suppose 5 experts is not a huge number sometimes, but for some things I'd have 5. But for one, which was the witness creation, it hadn't been done before. We had no data, so I had to rely on the person in our team that implemented the specification for a witness and the data that he generated from that. So although it was empirical data, it was really his implementation that I had to rely on. But yeah, for the rest of it, and the mass elicitation where you talk to the whole community, that was a new experience for me as well, which was fun.
Thank you, Sandra. And thank you all for speaking in this session and in the previous session and in general in conference. I think in the conference today and yesterday, it was great.